Good afternoon and welcome to today's Society of Fire Protection Engineers webinar entitled Designing and Deploying Aspirating Smoke Detection in Harsh Environments. Entitled Application of Fire Detection Technologies in Today's Data Center and Communications Infrastructure. My name is Morgan Hurley and I'm the Technical Director of the Society of Fire Protection Engineers. Today's webinar is sponsored by Xtralis. I'd like to remind all of you that if at any time you experience audio difficulties or problems advancing the slides, simply press your F5 key to refresh your webinar console. I would also like to encourage all of you to ask our panel questions. As a question occurs to you, simply type it into the box on the left-hand side of your screen, and we'll address as many of your questions as we can at the end of our presentation. The Society of Fire Protection Engineers will provide attendees 0.1 continuing education units for participating in today's live webinar in its entirety. Current SFP members will be able to receive continuing education units free of charge. Members will be required to provide their membership number. Non-members will have the opportunity to purchase the continuing education units for $25. To access the continuing education unit environment, click on the appropriate link located on the left side of your console at the end of today's presentation. Links to these environments will also be sent to you in the thank you messages that we will send you following the webinar. Continuing educations will be available units will be available for only 48 hours after the live event, and you will be required to answer a few questions based on the content of today's webinar. Please access these links only at the conclusion of the presentation. Now let me introduce today's presenters. Stephen Joseph has spent the last 11 years of his 21-year career in fire protection focused on deployment of detection technologies, most notably air sampling type systems. Throughout his career, he has held various positions with duties and responsibilities that have taken him across a vast range of industry segments, gaining him exposure of the fire risks and challenges associated with each. Along with his electrical engineering, marketing, and business management background, this exposure has allowed Stephen the opportunity to uniquely address fire detection needs of industry, which has included leading corporations across North America ranging from telecommunications, semiconductor, power generation, to oil and gas. Stephen has participated within code development communities over the year and is active in various industry associations and organizations such as NFPA and SFPE. Stephen currently serves in the position of Director of Industry Development for Xtralis, the leading manufacturer of VESTA air sampling smoke detection systems. Wes Marks has worked in the fire and life safety industry for over 11 years with a focus on air sampling, smoke detection, gas detection, and open area smoke detection. Wes has held a variety of positions at Xtralis, including applications engineer, product management, product support, and he's currently the regional sales manager for the Northeast. Wes actively represents Xtralis on the NFPA technical committees for NFPA 232 on record storage centers and NFPA 92 on smoke management systems. Wes has a BS degree in mechanical engineering from Worcester Polytechnic Institute and acts as an active member of NFPA, SFPE, AFAA, and NYFAA. With that, Steve, the floor is yours.
Great. Thank you, Morgan. Hello, everyone. Thanks for the introductions. And with this, we'll go ahead and get started. All right. Our presentation today focuses on fire detection solutions for datacom infrastructure. Now, that's a term, datacom, that we'll use throughout the throughout the presentation, and it's describing various IT and communication facilities, including but not limited to, such things as internet data centers, enterprise data centers, co-locations, computer processing rooms, telecommunication facilities, cable provider hub sites, satellite broadcasting facilities. So I just wanted to preface that as you'll hear that term datacom, and that's what we're representing. So during this presentation, we'll introduce and discuss the dynamics of the IT and communication industry, the fire risks in datacom environments, detection issues, various detection technologies, application solutions, and specification and design of fire detection type technologies. So as we look at industry transformations, over the past 10 years, the volume, velocity, and variety of data has and continues to grow at staggering rates. New visual and audio file types, increased computing power, unprecedented ways to communicate, more ways to connect and stay connected to the internet are drawing in subscribers, driving industry growth. So as a result, we have seen tremendous transformations occur throughout the IT communications industry, resulting in significant convergence, of industry and infrastructure. The lines are getting blurred as to the difference between IT and communication operations, and the facilities are becoming to look, and operate very similarly, as one example. We're also seeing major transitions in configuration and construction, with new generation power and cooling methodologies being introduced, and where deployment is more scalable. So consequently, networks require greater security, storage capacity, more in-depth processing to support their expanded roles, and performance and reliability expectations are higher, and the pressure to deliver efficiently and effectively has never been greater. So in an industry survey, the top three concerns were monitoring, heating, and network availability. So many in the industry are realizing that monitoring and management systems are essentially essential in ensuring availability, improving efficiency, planning for the future, and managing change. So what we want to focus on here is the number one concern, monitoring, which in fact is the subject matter of our presentation. So the growing dependence on datacoms means growing consequences of downtime and also diminishing tolerance to downtime. A study last year by the Poneman Institute found that data centers average about approximately 2.5 outages per year, with an average outage duration of about 134 minutes. So if that trend is tracked over the global footprint of more than 500,000 datacom facilities worldwide, it works out to about 2.84 million hours of annual data center downtime. So what's the cost? Cost of downtime? Well, if we look at one source, that being the FCC, who estimate that the cost in a large datacom facility is upwards towards US $2 million per hour. That's pretty significant when you take that across the total number of hours globally of downtime. So what contributes to that cost? We look at such things as service, interruption, disruption to business, service, and customers. Obviously, the financial impact, revenue, profit, accounting procedures and processes, transactions, and obviously the effective reputation, that being business to business, consumer, government, agencies relying on the reliability of the network, internal workers having their networks compromised in terms of doing their work, and of course equipment, latency, loss of the equipment, and of course facility, damage of contamination of the building of other physical structures. So given that the consequences can be extreme, the importance of protection systems continue to grow in datacom facilities. And with that, we look at the various fire risks. The most common instigator of fire events in datacom facilities are building systems. This includes, but is not limited to, such things as electrical systems, which might include power distribution systems, shorts, overloading, component degradation, or other electrical system malfunction. You can also look at overheating of cabling components and equipment result in combustion of polymers, which, when released into the environment, release toxic and corrosive gases that over time may damage electronic devices. Also mechanical systems, such as HVAC systems malfunctioning. HVAC systems also spread in the aid of circulation of smoke and gases to other compartments, and this ultimately can lead to damage of electronic devices and other compartments. We also look at the risks of generators, fuel lines, exhaust lines. And let's not excuse administrative, such as bad housekeeping and storage practices. And when we look at densely packed arrangements of equipment and fuel sources, this will encourage the spread of fire and smoke contamination within these types of environments. So what are the detection system expectations? Automatic fire detection systems play an essential role in the overall fire protection strategy. So to effectively address all needs, they're relied upon for such things as communications. And what we mean by communications here is alerting personnel of abnormal conditions being the first line of defense against a thermal or a non-thermal threat. Also look at intervention, and that is the opportunity to investigate pre-alarm conditions. Initiation of sequential systems or procedures such as fan shutdown, suppression release, transfer of data, and so forth. And also the minimization, and that is early response will likely reduce the impact on operations. So for instance, may not have to shut down operations, senior management may not have to get involved, and the fire department may not have to come out. And that's the intent of automatic detection systems. Ineffective automatic detection systems can break the sequence and not meet stakeholders' response expectations. So on this particular chart, fire progression, we look at the various stages of fire, which is comprised of 4 stages. And this includes the incipient, growth, fully developed, and decay stages. So as we look at the incipient stage, which quite frequently could be the progression of equipment or component degradation or failure, overheating of cabling, and similar such events, in some cases it could occur over the course of hours or even days before the outbreak of flame ignites. The smoke development in this stage is generally not visible to the human eye, has considerably low heat release rates, being extremely buoyant, with migration easily influenced by air currents. If we follow the incipient stage, we get to the growth stage, which could be expected to increase quite rapidly, leading to the fully developed stage, which is generally the case. As fires grow in size, the energy release rate increases to peak value, and once fully developed, fighting fires become significantly more difficult, and of course the consequences potentially much more severe. Smoke detection categories will be related to how far an event develops before it is detected.
Excuse me, Stephen, could you speak up some? Some of the attendees are having a difficult time hearing you.
Sure, I will. Thank you. Thanks for that. All right, so as we look at detection classification categories, there are essentially 3 sensitivity classifications used by the industry. They are standard fire detection, early warning fire detection, and very early warning fire detection. Parameters regarding each classification are primarily defined by sensitivity and spacing. So here on this chart, we've shown relationships diagrammatically as to the relationship of the various sensitivity classifications as they lie on the chart. And so as we see spacing as being much less dense for standard fire detection, it would follow the sensitivity is lower for standard fire detection. And conversely, as we look at very early warning fire detection, sensitivity being high, very sensitive, and with spacing being much more condensed, more spacing, or less spacing between each device. So to be more specific about these categories, let's first focus on standard fire detection, as we've shown in this chart here. So as we look across this particular category of sensitivity, or classification of sensitivity, let's begin with the alarm sensitivity. And that's typically that's stated by a device listing, but generally around 2.5% obscuration per foot for this specific sensitivity category. Spacing is generally about 900 square feet maximum, but may be less depending on air exchange rates and other specific construction parameters. Coverage of mechanical air handling units is generally applied in accordance with relevant standards such as NFPA 90A and B. And so relevant to aspirating smoke detection technologies, we see an additional column here, transport time, and that is the time that smoke is introduced at the very last sample port of an air sampling type system, at the time that that smoke is transported back to the detector. In this specific sensitivity category, that time should not exceed 120 seconds. That gives you an idea of the classification of standard fire detection. So next we look at early warning fire detection. So this is an installation concept that was developed by the telecommunication industry in the early 1970s, and is based upon reduction of spacing, thus increasing response time of detection. So under this classification, alarm sensitivity is typically that stated by the device's listing, but generally around 1.5% obscuration per foot. And when you look at spacing, spacing is now reduced from standard fire detection, which was 900 square foot, down to 400 square foot maximum, but maybe less depending on air exchange rates. The coverage of mechanical air handling units, similar to standard fire detection, is generally applied in accordance with relevant standards such as NFPA 90A and B, and as well relevant to aspirating smoke detection systems. So as we see smoke transport time test go from 120 seconds down to 90 seconds for the specific sensitivity category. So what you're seeing is a more performance-based approach in regards to this specific classification of sensitivity, if you would. The next on the list is very early warning fire detection, which refers to a classification of fire detection intended to detect incipient, low-energy fires before fire conditions threaten services. Application of very early warning fire detection, is referenced most notably probably in NFPA 76 is one of the main standards, and that is the standard for protection of telecommunication facilities that give reference to very early warning fire detection systems. And given the characteristics and criticality and uptime objectives of mission-critical facilities, the recognition and application of very early warning fire detection has been widely adopted internationally as well across industry segments. And so for very early warning fire detection, alarm sensitivity is specifically 1% obscuration per foot. Now I might note, and this is relevant to each and every one of the sensitivity classifications, that sensitivity is at the port, at the detector or port, meaning that each and every sampling port must be at 1% obscuration per foot or better under the sensitivity classification. So unlike the previous two classifications, very early warning fire detection requires or is expected to provide a pre-alarm signal. So we haven't seen that in the other sensitivity categories, and this is specifically set at 0.21% obscuration per foot. And when we look at spacing, so we've come down from 900 square feet for standard fire detection, 400 square feet for early warning fire detection. We're now down to 200 square foot for very early warning fire detection. But it may alternate as well. I mean, under certain configurations, we may see that the very early warning fire detection systems alternate between high and low drops every 400 square feet, but no less than 200 square foot between levels. And this is intended to address congested areas where obstructions might occur, and that the intent is then to provide sampling or detection above and below the obstruction. And in doing so, the spacing alternates every 200 square foot. So in reference to monitoring mechanical error, unique to this classification of detection is a requirement to monitor at multiple points throughout the environment, and this is particularly at return air and transfer grills. And since the rate of smoke generation in a smoldering fire is relatively small and the airflow velocity in a room is generally quite high, the movement of smoke is dominated by the airflow of the mechanical systems. So furthermore, smoke generated during the incipient stage, it's not hot and therefore has very little thermal lift. It's cooled by the air velocities. This often prevents smoke from moving directly to the ceiling, causing smoke to dissipate more widely. And similar to the other sensitivity classifications, when we look at aspirating type smoke detection systems, we'll have that category of transport time. And you've seen it gone from 90 seconds for early warning fire detection down to 60 seconds for very early warning fire detection. So we've now learned the three detection classification categories, and our next step is to understand the various detector technologies that fall into each category. These are essentially, there's essentially four types of smoke detection technologies that we'll consider in this discussion as we're talking mission-critical data center telecommunication. And with that, we look at such technologies as beam type detection, and when we see beam type detection, we look at the standard fire detection category in terms of its ability, in terms of sensitivity. And then the next on the line is conventional spot type smoke detectors, and this might include the likes of photoelectric ionization type smoke detectors. And with this specific category of detector technology, we'll see it line up in the standard fire detection and early warning fire detection categories. largely based on its sensitivity characteristics and ability to perform its intended function at those sensitivity ratings. And the next on the list is reference to laser spot type smoke detection. And this category of detection is as well a passive spot type detector. Its sensitivity capabilities will allow its operation within the very early warning fire detection mode. Now, you won't see it checked off in the other categories because of its sensitivity characteristics and such, that it remains in the very early warning fire detection category. And then the next on the list, the final on the list, is aspirating laser-based smoke detection technologies. Now, we'll see that across the entire range, standard fire detection, early warning fire detection, and very early warning fire detection. And the reason for that is because of the sensitivity range of those the specific technologies that allow its operation in each and every one of those sensitivity categories. And it's just a matter of spacing the sampling ports in such a manner that you achieve the desired sensitivity category, if you would. All right, so selection is based on the technology's suitability to effectively perform its intended function within the sensitivity objectives. So we look at the various technologies on this particular chart and how they line up in regards to their capability of detecting at the various sensitivity category. And as we see the lineup, we see the various placement in terms of technology to performance. And what we're getting across in this particular graph here is that, just because a specific detector can operate in a specific sensitivity category doesn't mean necessarily that its selection is suitable for the particular application that you're considering. So you've got to look at other factors contributing to selection of detection technology, and that might include, suitability in terms of its performance under various environmental conditions, reliability, its predictability in terms of its performance under various conditions, dynamic conditions that may be prevalent to datacom type infrastructure, its ability to avoid faults and provide reliable operation from fault tolerance, ability to provide analytics, providing more information to the user about the environment for operational efficiencies. A next category of consideration might include, impact to operations when installing, or perhaps testing and maintaining the system, getting to the detector to maintain, test, and inspect it. And of course, compatibility of the detection technology to other systems or communication systems within the facility to bring all the communications to a point where it can be managed and controlled. Obviously, we look at such things as accessibility during and after installation, which is similar to the impact of the operations when installing, but we now look at it in the respect of getting to it after it's been installed. The maintenance requirements and frequency, its obsolescence-proof, ability to be obsolescence-proof, and the return of investment life cycle costs. So all these are kind of bundled up into this category of factors that one might choose in terms of selecting a specific category. So if we look across the chart here, we see various technologies mapped out on the chart in terms of what their potential in terms of performance would be for the various expectations in the environment. All right, so detecting smoke in datacom environments using conventional prescriptive methods, technologies, placement, and spacing can be challenging, in some cases, if not impossible. I'll describe that. But the unique environment within datacom infrastructure presents a challenge to both early and reliable fire detection, and detection is made difficult because, first off, airflow patterns. Airflow patterns in datacom infrastructure is often turbulent, unpredictable, and may direct smoke in directions not conducive to conventional detector placement. So given these dynamic variables, certainty of smoke reaching conventional passive technologies presents various performance challenges. We then look at air velocities. Airflow interferes with the normal dispersion of smoke, as can be seen, in this particular illustration, two illustrations. If you compare the two illustrations, it's quite apparent to see the behavior of smoke under a low velocity condition and its performance under a high velocity condition. So the resulting effect is reduced predictability of conventional detector performance in high air velocity environments. So since the rate of smoke generation in a smoldering fire is relatively small and the airflow velocity in the room quite high, we look at the movement of smoke, which is dominated by that airflow in the mechanical systems. And then, as we mentioned earlier, the effects of smoke being cooled by the airflow has very little buoyancy to get it to the ceiling. This often prevents smoke from moving directly to the spot detectors that reside at ceilings where they perhaps would be located, causing smoke to dissipate more widely. So on certain cooling configurations, air velocities are also exceeding conventional detector-rated listings. So a variety of challenges when you think in terms of airflow patterns, and airflow velocities. But we also look at air circulations. The dynamics of air circulation also present a challenge for reliable smoke detection. So take, for instance, recirculation modes. Let's break it up into two modes, recirculation mode and a growing use of economization mode. So if we look at recirculation modes, with each cycle, smoke enters the HVAC system. And remember that smoke is certainly in an incipient condition. Little buoyancy follows the airstream. First place it's going is to the HVAC system. So once in the HVAC system, undergoes a degree of scrubbing as a result of filters and an introduction of makeup air contributing to the dilution of smoke. And so if we look alternatively then at the other problem, and that's the use of economizers, which is great in terms of efficiencies for the facility, in terms of taking some advantage of natural cooling or free air cooling in that respect. It presents some challenges for the reliable detection of smoke. So we'll take this illustration, and if you can just imagine here that if we take a large intake of fresh air rushing into the facility, and that the same effects of that air has on the smoke in regards to migrating the smoke to the exit path of the air, which is generally going to be exhaust dampers leading the smoke out to the environment or to the atmosphere. So if we look at it from that respect, what we're doing is we're taking any fire incident and we're taking that smoke and bringing it right out to the environment or to the atmosphere. We're not getting the recirculation. We're not getting the homogeneous mixing of the smoke in the space. And what happens is we have a highly diluted sample of smoke not making it to the ceiling, going directly to exhaust ducts, and never having the opportunity to be detected. And that's the risk in terms of what economization has in terms of performance of smoke detectors, or the expectation that smoke detectors would respond in those various conditions. So with that, we have to consider those as part of the challenge. All right. Next on our list is congestion, congested spaces. So as we look at fully, partially enclosed cabinets and structures, loaded cable trays, process piping, ductwork, and other obstructions, they all impede smoke delivery to conventional passive spot-type detectors that might reside at the ceiling. So imagine in this installation, you have your smoke detector at the ceiling, fully loaded cable trays, process piping, ductwork, and all the other things that go on the ceiling. We start to think about things in regards of smoke delivery. So smoke actually getting past the obstructions can be expected to be impeded. In fact, various codes, as I mentioned, NFPA 76, for instance, looks at that as a potential risk and talk about, from a performance objective, placing sampling below or detection below the obstruction. So that configuration we talked about earlier, high-low drops, where you have a sample port or detector above the obstruction and as well below the obstruction. But the intent here is that it is a challenge for the environment, as can be appreciated from this image here. So obstructions present significant challenges as well for accessing conventional detection technologies once installed, significantly contributing to their cost. So if we try to place that smoke detector above the obstructions and then later try to get to it to test and inspect it, as will be required annually, we can appreciate the fact that we'll add some additional cost to have to get to that detector, or perhaps maybe just couldn't get to the detector, period. So accessing conventional detectors above or near obstructions for annual inspection, test, and maintenance may be very much difficult, but it also subjects the network to potential outages. In other words, getting personnel above those equipment, above the processing equipment, or above mechanical systems in that respect, puts a certain level of risk to the operations. So, with this particular picture, this is quite surprising to see this application, but what we're trying to show here is that this application is kind of like fitting a square peg into a round hole. And so, here's an application where the intent was to detect smoke coming into the HVAC system using conventional detectors, or a traditional approach, if you might say. And the point here to be made is that there's a missed opportunity, and that's an opportunity to take advantage of design efficiencies using appropriate technologies, resulting in lower return of investment, and plus supervision. I mean, the fire panel has no idea that the dust covers are on these detectors. It's fat, dumb, and happy sitting on the wall thinking everything's okay. So there's some definite missed opportunities. We also have some compromised goals. Response objectives are missed. Minimized maintenance opportunities, minimally intrusive, as we talked about, getting to these detectors to maintain, test, or inspect, or getting to the HVAC system to service it in that respect. So we have a number of objectives that have been missed. These particular detectors may be challenged in regards to its performance and their air velocities. So, the objectives in terms of sensitivity, and given a very sensitivity classification, which was probably the intent, may be compromised because of the performance of these detectors in terms of how they're installed. We first look at the orientation of the detectors and see that they're upside down, which is outside of that approval or listing. In respect to its performance, we can't be sure or certain that it will respond to its intended function. So with that, suitability is questioned. Outsiders will question the suitability, such as owners, users, insurers, and of course, reputations of the engineer, designer, the firm, installer, are all at risk. And so this is, a good example in terms of a misapplication of technology, if you would, to meet a particular objective. So, with the various transitions in terms of the industry and innovations, we're outpacing traditional approaches by the virtues of the industry transitions. The applications are outclassed by technology innovation, so we're bursting the bubble in regards to application of traditional methodologies in these types of applications where, placement, spacing, suitability is all questioned in regards to the detector's performance under these various scenarios. This might be a hot aisle. Temperatures may be in excess of 120, 140 degrees. Velocities might be such that they're outside of the listing or the parameters of the detector being applied. Finding a location to mount the detector all become questioned, and that's as a result of the innovations that are occurring in the industry, not keeping pace with the prescriptive measures that we're applying in these various environments. So here we have an example, a kind of situation we were discussing in previous slide, using traditional detector placed on a ceiling. While this appears fairly ordinary and acceptable use of the detector, when we look at the application, we can see through, although in the actual facility that it's in, the space that it's monitoring, there's a performance gap that will be evident. So the performance gap is due to the environment, which may include airflow patterns, velocity, circulation. In addition, the high ceilings, likelihood of stratification will further aid to the impediment of smoke. And in general, the effectiveness of the installation will not likely meet the performance expectations of the owner. Secondly, trying to think about how do you get to that detector to maintain, test, and inspect it on an annual basis all become questioned. That brings us to a discussion of ASD suitability. So if we consider aspirating smoke detections for this environment, the previous environment, we'll find that the technology possesses characteristics that overcome the challenges of a datacom environment. These features include sensitivity, very early warning fire detection, which it will include very early warning fire detection, active versus passive detection performance, its capability, the fact that it's unaffected by airflow or temperature extremes when properly designed, cumulative detection performance, meaning that more than one sample port is likely to see smoke and bring that smoke in a cumulative fashion back to the detector, absolute smoke detection with fixed calibration, meaning that when we set the sensitivity settings in the detector will perform at the sensitivities they've been designed for, and predictable detection performance. And when we talk about flexibility, we talk about the idea of having multiple alarm thresholds to stage responses, or the idea of flexible sampling configurations, or the ability to place the sampling in environmental conditions such as, high temperature environments that will otherwise impede performance of traditional measures. Simplicity, the fact that it's low maintenance, ease of maintenance, the accessibility of it is greatly improved in regards to traditional measures, as we'll show in some preceding slides. And as well, the security, and that is the accessibility without disruption of operations. The fact that, to get to the detector, to test, inspect, and maintain it, it becomes a lot more manageable in the respect of its application. So in addition, the ASD air sampling detection offers exceptional performance as demonstrated in the primary system metrics, which include certainty of measurement, and that is absolute high stability fixed calibration, alarm thresholds between 0.0015 and 6.4% obscuration per foot, optical light scattering detection principle using a solid-state laser light source. And we talk about operational stability and the fact that higher tolerance and rejection of nuisance alarms caused by dust, steam, insects, and so forth, and high stability optics. And system integrity, the fact that active monitoring of all critical detector functions occurs, such as flow, optics, calibration, and the fact that in some systems optics are automatically cleaned, requiring no drift compensation techniques or requiring no calibration of the detectors once installed. And so to bring in the point about detector maintenance, ease of maintenance for these types of detector technologies, we talk about ease of access and the fact that the detectors can reside down on the wall. You bring the very last sample port to a location where you can easily just walk up to it to test and inspect. The intent of an air sampling type system per codes and standards is that you do the smoke transport time from the very last port back to the detector, and you satisfy the requirements for test and inspect of these types of systems. So greatly reduces the overall impact in terms of test and inspection in a highly congested or problematic area in regards to getting to the detectors once installed. So here's an example. I mean, we've taken this example to kind of show a return of investments, and what we've done is just essentially taken, for instance, 12 rooms at approximately 7,000 square feet each with the sensitivity objectives of 200 square foot spacing for very early warning fire detection. And so when we take that and we do a comparison between spot type detection and air sampling, aspirating type detection technologies, we'll see that there's some exceptional, unsurpassed return of investment. And so you take the 440 spot type detectors, each requiring to be accessed for test and inspect, particularly in a datacom type infrastructure, which may present some challenges in terms of accessibility, but nonetheless, you take each and every detector, you make some assumptions in terms of labor costs and time to test and inspect each sample port, and you compare that, you come up with $8,470, which is quite conservative from that perspective. And we take the same comparison with 12 aspirating smoke detection detectors to serve the same space. And again, the test and inspection only occurs at the very last sample port of each pipe run. And with that, you have a comparison at $1,119, about an 86% savings. So that presents itself as a significant return of investment for these types of technologies. right, so as we start talking about application now, we look at various applications in regards to where you place sampling. And so we've put this graph together, or illustration together, that kind of shows the ideas in regards to where you put various sampling locations. So this is how ASD overcomes the obstacles of the environments by monitoring locations at multiple locations within a space. So a good design will consider a holistic approach with multiple sampling locations throughout the space. And the point we're making here is that the further you get from the source, the greater the compromise. So if we look at the cabinets, for instance, sampling within the cabinets would be ideal. And if you didn't decide to sample within the cabinets, the first place that smoke would migrate to under this hot aisle configuration would be to the return, the ceiling return plenum. And so placement of sampling within the hot aisle at that point presents an opportunity to detect at that location. Now you're making a little bit of a compromise there because you're not able to identify which cabinet, but you're able to identify that one particular cabinet in this particular row had an incident before it got up into the air plenum. Now, if you passed the air plenum and you went to the return point of the HVAC unit and decided that that's where you want to put your detection, that being point C, the return plenum, point D, the HVAC return, and if all you did is that, you wouldn't have clarity in terms of knowing which containment aisle. You'd know that there was an event. It may be further along the smoke growth chart, but you are potentially going to detect it with a very early warning fire detection system. So the point I'm making here, rather than going through each and every point here, is that the further you get from the source, the less clarity you have in terms of where the ignition source occurred. And so it's best practice is to consider multiple points, and as such, you have more clarity in terms of where the source originated. You have more control, more potential to have surgical power shutdowns, suppression release in very specific zones. And so there's a lot of opportunity by having multiple locations. And the following slides here are just some examples of that very same configuration in regards to, well, each of them show a different configuration of different hot aisle configuration, just to show, as you'll see, a common theme for each and every one of these examples, that we're following the airflow. And that's the beauty of an air sampling type and aspirating detection technology, is that you can place sampling at the locations where air is going to gather and use that as a logical location for sampling and detecting smoke. So in this configuration here, we're detecting it before it gets to the ceiling. We're also detecting it at the return air path. We're detecting it at the supply side of the HVAC unit. If there's an event in the HVAC unit, we potentially want to detect that before it spreads smoke through the rest of the data floor or data hall. And so just more examples of the same. And as you can see, we follow kind of the same scheme throughout with the same methodology in regards to follow the air, place detection at the most likely sources where smoke will migrate. And just one more illustration in that respect. But all, again, it's the same theme. And so, as we look at the common application areas, we look at telecommunication switch rooms, server halls, containment aisles, modular data centers, mechanical spaces, potential for monitoring within generator rooms, power distribution centers, battery rooms, and cable vaults, and of course operation centers, containerized data halls, and cellular satellite facilities, closed CEVs, other remote infrastructure. The ability to provide the various detection at each and every one of these types of areas. Now let's look very more specifically at the typical monitoring solutions for each of these types of areas, which is somewhat of a summary of what we've talked about in the previous illustrations. But we look at ceiling detection, and that is placement of the sampling pipe at the ceiling for area detection. And again, that might be at every 200 square foot. And here's multi-level detection, the idea of detection at the ceiling and below cable trays. And the idea is that we're still very early warning fire detection under the scheme where we're sampling 200 square foot, but alternating every 400 square foot, 200 square foot between sampling port high and low, with the ability to detect below obstructions. Above ceiling and below raised floors, the idea that, again, trying to get to the detectors to maintain, test, and inspect them could be challenging using traditional means where the air velocities may be outside the range of the detectors. So the idea of utilizing an air sampling type system or the convenience of accessing the detector in an accessible location might be of concern. Return air, as we've talked about, the idea of monitoring various points such as return air paths, transfer grills, even that supply side of HVAC systems. And as well, the idea of monitoring fresh air intakes. So we're monitoring then the quality of the air coming into the space to make decisions about that air, which may be smoke-laden, contaminated, and we don't want to bring that environment to the facility. So we're using these types of technologies that can provide more analytics, higher sensitivity, and potential for detecting contaminants coming into the space to make logical decisions with the building management system for either recirculation mode or economization mode under certain conditions. There's a growing trend. And as well, the idea of monitoring containment aisles, the idea of placing the sample pipe at the exhaust path of the containment aisle to detect smoke coming from the racks themselves. And within cabinets, as we've touched on, the idea of bringing the sampling to partially fully enclosed cabinets to monitor within the source. And with that, we also consider other threats, addressing other needs such as gas detection. The idea with these technologies to be able to simply add an additional sensor onto the detector, utilize the existing pipe network to now monitor for the variety of gases, whether they be flammable, corrosive, toxic, with the intent of being able to use that pipe network as a delivery system to have a distributed sampling arrangement to detect such spaces as battery rooms, cable vaults for methane, battery rooms for hydrogen, and other configurations where hydrogen, oxygen, or the corrosive gases, or for that matter, the toxic gases may be of concern, simply by utilizing the pipe network, adding a simple module onto the pipe network, and having the expanded capacity to monitor for various gases. And so designing and specifying aspirating detection systems, we look at various things in terms of what we would consider the appropriate method in terms of designing. So with that, properly designed air sampling aspirating detection system is paramount for the proper operation of the system and meeting fire protection objectives. So the design specification should take into consideration qualifications of designers, installers, and commissioning technicians, ensuring that they're authorized, the particular manufacturer's brand. Apply coverage techniques that will account for all possible smoke migration paths we've touched on some of the illustrations, never exceeding limitations specified in product data sheets or design guides. Maximize coverage by utilizing combined coverage techniques where possible, and that is potentially utilizing the detector to monitor multiple points where it has the capacity. Ensuring system design meets manufacturer's criteria, local jurisdiction, and requirements, and by including manufacturer in early stages of project work. So improving the field experiences, we talk in terms of standardization, and that is adopting a master aspirating detection specification template when applying these types of detectors, or whichever type of detector is being applied, ensuring that there's standardization in regards to how it's specified. And again, qualification, can overemphasize the use of qualified system integrators, and coordination, and that is notification of projects early on while in the planning stages, keeping the manufacturer in the loop, require manufacturer's design review prior to submittals, will all help and aid in terms of improving the experiences in the field and ensuring consistency site from site. And so with that, in summary, as we touched on, industry is in a flux. We're seeing quite a bit of transitions and convergence, special requirements of the environment such that traditional measures and solutions have been outpaced and outclassed by technology innovations. And that aspirating smoke detection systems is the alternative in terms of meeting some of those, overcoming some of those obstacles and challenges within these environments. And that the successful application considers various parameters such as the specification templates, specification requirements, qualifications, and all lead to the element of success for the application of these types of technologies. And as we touch on next steps, educate yourself. There's a variety of tools and resources available in the marketplace on these types of technologies, and leverage manufacturers' experiences for support to help you aid you through your next project. And with that, I thank you very much. I am done with my portion. Turn back to you, Morgan.
Hey, thank you. Excellent job. A few of you have already submitted questions, so we're going to jump right in. While your questions are being answered, please take this time to answer the event survey, which can be accessed by the red icon in the widget bar at the bottom of your screen. Also, you may use this time to access the CEU environment by clicking on the appropriate link located on the left side of your console at the end of today's presentation. Okay, so what I'm going to try and do is hit some of the questions that have been asked by multiple folks. So let's start with one that addresses coverage area. You talked about coverage areas like 900 square feet and 200 square feet. Is there a way that one can kind of engineer the coverage so that they achieve specific fire protection goals? And one area where that might be particularly important might be one where there are high airflows.
Yeah, right. So I think Steve covered that in his slide, going through the different categories for standard fire detection, early warning, and very early warning detection, and to look at the spacing coverage requirements. So for standard level of fire detection, you'll be looking at 900 square foot spacing. Early warning, 400 square foot spacing, and 200 square foot spacing for that very early warning detection. Now, as far as for airflow, doesn't play into that categorization for air sampling system, as it's a cumulative system, and for a very early warning application, 200 square foot is really the recommendation.
Okay, excellent. Thank you. And another question that was asked by a few folks had to do with the discussion that you had on life cycle costs. And I guess there are some questions that had to do with what elements were included in those costs. So could you expand on that a little bit?
Yeah, sure. Well, let me go ahead and take that, Wes. So I prepared some of that exercise. So, what we considered with that particular exercise is we looked at, first of all, how long it would take to test and inspect spot-type detectors. And so what we took is an average of 15 minutes per spot detector, given the environmental characteristics of telecommunication data infrastructure. And what we said there is a labor rate of $110. And across 440 spot-type detectors gives you an idea of where we started with spot-type detectors. Now, when we looked at air sampling-type smoke detectors, we took the idea of taking the very last sampling ports on each and every pipe branch, trying to remember how many pipe branches. I think it was 16, but don't quote me on that. It was a specific number of pipe branches across the number of detectors. And with that, we applied a time element to test and inspect in each and every last sample port of a pipe run. And then we also looked at, because this is different than traditional conventional spot-type detectors, we have to look at power supplies, testing the batteries of the power supplies. That was included. Testing the alarm communications to the fire panel. That was included. Doing a visual inspection of the pipe network. That was included. So we did all these various elements that you wouldn't necessarily do on a traditional spot-type detector to be conservative and have a very conservative number from that respect. So that, I hope, answers the question. And we have that exercise, and we're very happy to share that exercise if somebody is particularly interested to see how that was done up in an Excel spreadsheet.
And presumably, just to confirm, the initial equipment costs are included as well.
It was a maintenance exercise, not necessarily a cost.
So that was just life cycle, the continuing life cycle cost.
That's exactly right.
Okay.
Life cycle cost of test and inspect.
Okay. Thank you for that clarification. There's a question that had to do with setting the different thresholds on an aspirating smoke detection system. Are there any kind of engineering correlations, or are those just kind of pick from the table type of exercise?
Well, there is certainly the table, but the key thing to understand is that those are effective sensitivity at the sampling hole for an air sampling system. So that's all calculated in a design program available from the manufacturers that will calculate how much smoke it would take at one sampling hole or a group of sampling holes to reach an alarm threshold at the air sampling detector. So it is definitely an engineered system.
I might just add to that a quick way of achieving that, if you take the target sensitivity at the sample port, so if we look at very early warning at 1% obscuration per foot, what you do with an air sampling type system is you take the number of holes on the pipe network or on the detector, since each and every hole introduces a certain percentage of error, so you have to account for that dilution, but you take the total number of holes divided by the target port sensitivity, and that gives you your alarm threshold. And that's essentially what the modeling program does to achieve that. So it becomes quite simple from that perspective. You just start with your target port sensitivity for the various sensitivity classification, and you divide that by the number of holes. If I said that right. Yeah. Okay.
Excellent. Thank you. And another question came in from a few folks has to do with when you do receive an alert or alarm from the aspirating smoke detection system. Is there any additional information that one would have in terms of the source of the alarm, or how would one address that?
Yeah, I think it's important, for the engineer when they're designing their system to take that into account when they're doing the layout. As far as Steve covered some of the different coverage areas, whether it's at the ceiling or in an underfloor space, or at the whether it's hot aisle or cold aisle containment, or at the return air. So, an air sampling system can identify the smoke source to a certain pipe, and to design the system so you can detect it to a certain area will certainly give you a better design. But with that said, a high airflow space is difficult to detect smoke because of the nature of the space, and there's not necessarily a correlation between where a fire would start and where smoke would end up at the ceiling. So it's a challenging environment, which is why you need a system that's highly sensitive and cumulative type detection.
Thank you for that. This is hopefully a pretty easy one. Someone had asked about piping materials that one would use with the aspirating smoke detection system.
Sure. So the pipe that's typically used is a 3/4 inch Schedule 40. It's a CPVC, so it's a fire-rated, plenum-rated tubing. And that typically would come pre-labeled or pre-identified as air sampling tubing. So other types of material can be used, and sometimes that's desirable if, for some reason they want a metallic tubing. The key thing, it's got to be airtight except for the sampling holes. It's got to be modeled in the design program, to model the airflow with those, with the diameter that's being used. And it's got to be properly identified, per NFPA 72. So there's different manufacturers have stickers, to identify the tubing as air sampling type tubing. But again, the most common type is the CPVC 3/4 inch Schedule 40.
Excellent. Thank you for that. One final question. Early in the presentation, when you talked about the different stages of fire development, you also mentioned transport time, and we did have a question asking for a little bit of clarification about what's included in transport time.
Sure. So the transport time, that's the time it takes air to get from a sampling hole back to the detector. So it doesn't include alarm time or time until the panel would go into alarm. So just think of it as air, as from when air enters a sampling hole until that air gets back to the air sampling detector, and that's the transport time.
Okay, excellent. Thank you. Well, unfortunately, I'm afraid that we have run out of time. So on behalf of the Society of Fire Protection Engineers and Fire Protection Engineering Magazine, I'd like to thank everyone for attending. I'd like to thank Xtralis for making today's event possible, and wish everybody a productive remainder of the day. Thank you very much.